Next up is resistors in series and parallel. Resistors in series and parallel. So we've introduced these basic building blocks of circuits: resistance, current, voltage, and we've also talked about some physical items that facilitate these things. Voltage can be provided by a battery or by a capacitor, which we talked about briefly before. Resistance comes in the form of specially made resistors, but it can also be provided by things like light bulbs, and everything has some amount of resistance, right? Current flows through metal wires that connect all of the items together in a loop. But you may already know that most circuits are much more complex than like a single battery connected directly to a single light bulb. If you opened up your phone or a computer, for example, you would see a really impressive network of all sorts of electronic elements connected together, really tiny scale, with tons of junctions. So now we'll start considering how circuit elements combine and what effect that produces on the circuit in terms of voltage, current, and resistance. So there's two ways to connect any circuit element. And we'll talk about resistors in this section, but this particular concept of how any circuit elements can combine applies to any circuit component, right? Voltage source, resistance source, any other exotic thing. The first way that you can connect things together is in series. So I'm going to try to keep to a color coding here. I know I reuse colors, but series is going to be green, parallel is going to be purple. So in series, so if we have resistor, call him R1, and you want to connect him up to another resistor, one way that you can do so is to connect it just end to end like this. Another resistor R2. And you can connect that to another resistor here if you want. R3, and so on, right? And presumably this would go, to the rest of the circuit, but we're just looking at this little segment. So when things are connected to end like this, then they are connected in series, such that if you were a charge traveling along this wire, right, if current is going this way perhaps, you would have no other way to proceed other than one by one through each item connected in this way. If you were a little charge here, right, called a positive charge moving this way, you'd have to go through resistor 1. And then when you got here to this point, there's nowhere to go except for forward through R2. And then when you got to this point, there's nowhere to go except for forward to R3. There's no junctions, right? You're just going end to end. And this is things connected in series. It's connected in a series. The word kind of makes sense, right? So one thing that's really important for things connected in series is that current is equal through all things in series. All right. Current is equal through all things in series. The second way that you can connect things, I'm going to use purple, is in parallel. Parallel. So here we might have, I'll use white. We might have our R1, our resistor 1, and we have resistor 2 below it here, and we might have our third resistor also. So this is R3, and we're arranging them in parallel such that we create a junction. So if we had current flowing this way in the circuit, an individual charge would have a choice at this junction here to either go up this path and go through this resistor up top, R1, or choose the middle path and go through resistor R2, or down here and go through resistor R3. It can't go through all of them simultaneously. It has to go down one or the other. And then there's another junction here where it combines and then continues on its happy way, right? So in this case, in this arrangement, we say that resistors R1, 2, and 3 are connected in parallel. And that's the name, right? They're in parallel to each other. They're running parallel to each other. I guess in this sense they're also kind of parallel, but they're parallel and next to each other. For circuit elements connected in parallel, the voltage is equal. So, voltage is equal across all things in parallel, right? So that's for things in parallel. Okay. So what that means, to just really kind of flesh this out, is that whatever the current is here, it equals the current here. Doesn't matter that it's already gone through something. It doesn't slow down or speed up. The current is the same. The way to think about this with a pipe, right, in our water analogy, is anything that is in series is the same pipe. And for this analogy, you have to imagine that the pipe can't bow out and become a wider pipe, right? It has to connect maybe, to some other pipe in some discrete way, right? So for a given pipe, it's the same diameter throughout, and this is one big pipe. And so whatever its width is, which is determined by the amount of resistors that are on that segment, that determines the width of the pipe in this analogy. Whatever it is, and the water flows according to the same current along this pipe. There's the same amount of water passing a given cross-sectional area of this pipe per time. Yeah, so that's things in series. Things in parallel, the way to think about that with the water analogy, is that at this junction point, it's like you're at some potential here, right? V1, we'll say, and this here is V2, and these things have to connect up. So there's some V2 down here, and you have some potential difference, and what you have is 3 paths to do so. So I wish I could pull this out into 3D space, but you have 3 paths in which to go this same route, right? Ignore the curvature, doesn't really signify anything, but this might be the path that R1 is on, this might be the path that R2 is on, and this might be the path that R3 is on. Curvature means nothing, just really 3 different paths to get from high potential to low potential. So it's like 3 different pipes, right? So maybe that's a better way to draw it. You have pipe 1, pipe 2, and pipe 3, right? And if R1, R2, and R3 are equal in the amount of resistance, then the widths of those pipes will be equal to each other. If they're not, then there will be different size widths, right? You can have different amount of resistance on these segments. This segment here itself, you might agree, is a series segment. Even though there's only one thing, you can consider each little slice of wire, right, as being in series with the next slice of wire, which is in series with this resistor. So between this junction and this junction, for each of these paths, the top one, the middle one, and the bottom one, everything is in series on that segment, on each of those segments. And so these are 3 quote-unquote series segments that are in parallel with each other. And those series segments have a given amount of resistance, which determines the width of their quote-unquote pipe, right, in the analogy. So that's the way to think about that stuff. That's the way to think about it. So the reason that voltage must be equal across all things in parallel, voltage is potential difference, and these things have to connect back up, right? So if a pipe is going to be a part of the circuit again, and the circuit continues at this elevation, You can't have some random pipe that's just pointing off this way, right? And it's like, connected to nothing off in La La Land over here. It's not part of the circuit anymore. It's just out there doing nothing, right? So if the segment is going to be a part of the circuit, right? Let me clean this up just a little bit. If the segment is going to be a part of the circuit, then it needs to connect back up, and at that point, it's going to have the same potential as everything else. And so therefore, the difference in potential, right? This would be V1, and this is V2. The difference, that hill, the slope of that hill, so to speak, is the same for all of the paths, path 1, 2, and 3. Yeah? It's also possible to have resistors arranged in both series and parallel, right? We kind of talked about how the slices of the wire can be thought of as being in series with each other, but you can have more than one resistor connected together along a segment, right? So here's an arrangement, an example, right? So this would connect to the rest of the circuit, right? Presumably, the assumption is that it's connected to some source, some EMF source, right? So if we have this arrangement, we have some resistor there, and we have some resistor here. Call this R1, R2, and then we can also later have some resistor after, right? And so R1 and R2 are in parallel with each other, but the combination of R1 and R2, if you take that as just a unit thing, that is in series with R3, right? Alternatively, here's another example. There's obviously infinite possibilities, right? But I'll go through some. If you have two resistors here, continues on, and then you have maybe one resistor down here. So we'll call this R1, R2, R3. So R1 and R2 are in series with each other. Their combination, or you can say both of them, are in parallel with R3. So if you're having trouble recognizing these arrangements and you're not sure why I'm calling some things parallel and other things series and it's not clicking, what you need to pay attention to are these junctions here. If there exists a junction and you put yourself in the place of an individual charge here that's traveling, if you have a choice to either go through one component or another component, then you know that they are in parallel, right? But if by traveling through the circuit you must go through both of them, an individual charge, right, must go through both of them, like here, the charge traveling through here must go through R1, and then it must continue on and go through R2. It can't, turn around and go through R3 at that point. There's no connection. It has to proceed from R1 to R2. Then you know that they are in series. So look for these junctions. Notice that there is an absence of any junction between R1 and R2. They're in series. There is a junction between R1, separating R1 and R3, and so R1 and R3 are in parallel, as are R2 and R3. So the next thing that we're going to talk about is how to deal with all of these, combinations of things. So we have certain formulas that apply when you have multiple resistors in various combinations. So resistors in series first. So resistors in series. I'm going to do this in white. Oops. Resistors in series add together a certain way, and resistors in parallel add together a different way. So to analyze the total resistance on a circuit, we have to find the combined total resistance of all resistors on the circuit, in whatever combination or arrangement they may be in. This may sound like a really daunting task, but it turns out it's not too bad, usually. At least it's not difficult. It's at worst tedious. So we have a formula for how to add resistance of resistors in series, and it is given by, I'll do it in white, R EQ, standing for equivalent, so equivalent resistance, is equal to R1 plus R2 plus R3 plus yada yada yada. Meaning that if R1 were a 5 ohm resistor and R2 were a 3 ohm resistor, and we were to add these two together, which are in series, we would apply this formula and we'd have 5 ohms plus 3 ohms is equal to 8 ohms, and that is the total equivalent resistance of those two resistors. Meaning that we could take this circuit and rip out R1 and R2, leaving R3 alone, and replace it with, so we're going to say REQ, replace it with REQ, which is an 8 ohm resistor, and R3, I don't know, we'll say it's 2 ohm resistor. 2 ohm resistor. And the circuit would be none the wiser. Whatever you had connected to the circuit, it would behave exactly the same. It is literally equivalent to have R1 and R2 as we had originally, or to remove them and put in its place their equivalent combined resistance of 8 ohms. That's the concept there. So now, resistors in parallel. I'm going to box this in with green here before we move on. Boom, boom. Resistors in parallel. All right. So if we have 3 resistors in parallel, just like we were looking at up here, I'm going to redraw it. R1, R2, and R3. Again, we're assuming there's some current flowing through, which would imply that there's some, connection like this. But there could be many other things going on with the circuit, right? Just like in chemistry, you kind of can just say there's the rest of the molecule that this attaches to at this point. This is kind of the same concept in circuits. We're just talking about the segment that we care about here. We can find the equivalent resistance of these 3 resistors in parallel with the following formula. So for resistors in parallel, we have 1 over R equivalent being equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on. Kind of bizarre, right? The first one was pretty straightforward, but this is definitely different, right? So this, when you add this up, that doesn't even give you R equivalent. Mind the fact that R equivalent is inverted, right? And so an equivalent way of writing this would be R equivalent is equal to R1 to the negative 1 plus R2 to the negative 1 plus R3 to the negative 1 plus however many there are. And then that whole thing to the negative 1, right? So to the negative 1 just means something in the denominator. So x to the negative 1 is equal to 1 over x. So this is a bizarre formula, but there's a reason. And that is how resistors add, like this. I'll circle in that one, or I'll box in that one because that's the one that's most often shown. But be careful to to invert the whole thing in the end to solve for actually the resistance instead of the inverse resistance. Okay, so one statement that I want to make about how resistors in series add, go back up here, is, and it seems kind of obvious to say so, but for resistors in series, R equivalent is greater than any R individual, or I'll say Ri, right? So I being a placeholder for R1, R2, R3, or however many there are, any of them, right? R equivalent, the total combined, is greater than any individual resistance of the of an individual resistor that you're adding together with others, right? That makes sense. I mean, it's R1 plus R2 plus R3, so that makes sense. Over here, in parallel, though, that's not the case. R equivalent is less than any individual resistance. Meaning, if R1 is 5 ohms, and it's in parallel with something else, doesn't really matter, then R equivalent is going to be, of that, R1 and the other thing that's in parallel, is going to be less than that 5 ohms, which is really unintuitive, right? So let me address that. So how does that make sense? So resistors are things that contribute resistance to the circuit, right? That's what I've told you. Am I a liar? The more the resistance of the circuit, the more the resistors that you add in parallel, now I'm telling you that the total resistance of the circuit goes down. So to understand this, we go back to the water analogy with our pipes, right? So we have a high potential here, we're gonna have a low potential here, and we're gonna say one pipe. I'll just represent it with a line, right? So let's now, so this is like, equivalent to just a circuit with one resistor on it, perhaps, right? You have to have some resistor to give the width of the pipe, otherwise it's just kind of undefined. All right, so now let's add a resistor in parallel. Let's do it like this. So we have a junction here, right? And so a charge can either take this path or that path. I'll do it in green because that is our current designator, right? But it can't take both. And then they each combine back up over here to then get pumped back around up to high potential by the EMF and go through the journey again, right? So that's our circuit. So what does that look like in terms of water pipes and potential difference and all this, right? Well, we've added, just like we were saying before, another pathway to get downhill, right? You can think of this as a reservoir of water, and there's some place to catch the water, and these are actually pipes. And let's see, we're using blue for resistance. Sure, these pipes have some width, of course, right? Because there is a resistor on here, right? So I'll say R1, R2, I guess this was R2 and this is R1, doesn't matter. So there is some resistance, it's not nothing. So there's some width to the pipe. It's not just an infinite amount of water that can flow unrestricted. But we've added a whole other pathway. So this original pathway here is still as much in use as it was before we added that second resistor. And now we've added the second pathway, which I've denoted for some reason R1, and the same amount of water is flowing in R2, and now we additionally have some water flowing in R1. Really should have switched those. But so we've added more ability for water to get downhill is the point. Even though that new ability, that new pathway, has some associated resistance. So in that sense, you're adding resistance to the circuit. The more important thing to focus on is you're adding a whole new pathway for water to get downhill, right? So you can think of, instead of, you can think of, if you have the high potential here and you have low potential down here, let's say we do away with the pipes, right? And there's just this massive, crazy flood, and all the water just gushed downhill, right? It just flooded down the hill. That's kind of like there just being like an infinite amount of pipes, right? So it's not restricted to any given certain line, right? So that would be kind of similar to like us having just like a ton of parallel pathways, right? Out to like billions of parallel pathways. Well, the battery would drain instantly, right? All the built up charge would almost immediately flow around to the negative charge. Even though there's a resistor on each of these paths, there's so many paths that the charges go from high potential to low potential almost immediately. Just like the water flows from uphill to downhill almost immediately. I guess in a flood, it's kind of a thing that goes over a period of time, but that's just because there's so much water, right? All right. So I guess if you really wanted to imagine infinite current there, because infinite parallel lines, then you would just imagine a block of water falling down in a vacuum, unobstructed by air resistance, just falling straight down. It would be going very fast. Okay, so I'm going to pause here, and we're going to pick up with an example.